Hello my friends and welcome back to the You Can Do TV channel. For the renewed and expanded Albisgüetli workshop of the Uetliberg Forest District in Zurich, only timber from the nearby forest was used. Designed by architect Caspar Farlander in collaboration with internationally acclaimed timber engineer Hermann Blumer, the project aimed to demonstrate the structural equivalence of beechwood to the more traditionally favored spruce. The construction was not only ecologically responsible, but also a technical pilot project exploring the structural potential of local hardwood. Approximately 100 cubic meters of beechwood were required for the project. Rather than harvesting new trees, the timber came from standard forest management practices. This sustainable approach aligned with the project's aim of utilizing locally sourced material to its fullest. Structural elements such as walls, ceilings, and roofs were constructed entirely of visible beechwood, showcasing its durability, aesthetics, and mechanical strength. By increasing the use of beech in construction, the project hoped to drive future demand, raise market value, and encourage broader adoption of this underutilized hardwood species. The structural system consisted of a combination of top wall and triaxial slab elements. These were carefully engineered to maximize the mechanical properties of beechwood. The processing began with debarking and cutting logs into specific lengths for intended applications, such as beams, top walls, and roof trusses. The wood was then carefully dried in winter conditions to minimize discoloration and internal stress, reaching an ideal moisture content of 12 to 14%. Some elements were kiln-dried at temperatures gradually increasing to 30 degrees Celsius to eliminate pests and ensure dimensional stability. The top wall elements were produced in Hochdorf by a specialized timber company. Boards were laser sawn, planed, and profiled for tongue and groove connections. Each piece was sorted according to its visible quality, ensuring that aesthetic surfaces faced the interior. The prefabricated elements were reinforced with OSB, oriented strand board, on the rear to improve form stability. After insulation with mineral wool and vapor control layers, each panel was finalized and prepared for transport. The accuracy of prefabrication minimized waste and optimized on-site assembly. Once the prefabricated components arrived at the construction site, they were assembled using a crane. Each panel was secured and interconnected to form a monolithic, airtight envelope. The entire assembly process was closely coordinated between carpenters, engineers, and architects, ensuring seamless integration and structural performance. Prefabrication allowed rapid on-site construction, reducing disruption and increasing precision. Another standout feature of the Albisgüetli workshop is its facade cladding, made from yew shingles. Unlike beech, yew is rare and even endangered in parts of Central Europe. However, Uetliberg holds one of the largest yew populations in the region, making its use in this project both symbolic and sustainable. The weather-resistant yew wood, with its pronounced grain and rich color variations, was hand-processed into 7 mm thick shingles. After air drying and cutting, the shingles were mounted using staplers, forming a robust and elegant facade. Despite the hardness of yew, which made mechanical fastening challenging, the result is a unique, vivid surface, ranging from light to dark hues. Because yew shingles are uncommon in modern cladding, the project serves as an experimental reference for future applications, helping to document how the wood behaves over time when exposed to outdoor conditions. The Albisgüetli workshop is more than just a municipal building, it is a statement about the future of sustainable construction. By employing local, diverse, and underutilized wood species like beech and yew, the project proves that ecological responsibility, innovation, and architectural quality can coexist. As a model for forest management, construction industry stakeholders, and architects alike, the workshop demonstrates how regional resources can shape the future of timber architecture. It also underlines the importance of integrated design and material sourcing in building resilient, climate-conscious public infrastructure. Genbach House, a leading Austrian company, offers innovative small housing solutions under the Micro Home brand. These modular homes have been manufactured in Upper Austria, using high-quality, environmentally friendly timber frame construction. Whether tiny houses, modular units, or mobile homes, Micro Home offers compact, fully featured homes with an emphasis on sustainable living. The homes are assembled in the factory and then loaded onto trucks and transported to the required location. Each microhome has its own space for living, cooking, sleeping, and bathing, providing everything needed in a minimal footprint. These tiny homes are not only space-saving and energy efficient, but are also mobile, allowing the owner to relocate the home if necessary. These homes are ideal for a variety of uses, including vacation homes, weekend homes, office space, guest accommodation, or seasonal travel. They offer these homes as a complete package, ready to use. With Microhome, they are redefining the way people live. Compact, mobile, and sustainable, all proudly made in Austria. Plywood is an engineered wood product made from multiple thin layers of wood glued together with an adhesive, with the grain of each layer perpendicular to the adjacent layer. This cross-grain structure provides dimensional stability, strength, and resistance to warping. The manufacturing process begins with the selection of suitable logs, usually softwoods such as pine or birch, or hardwoods such as eucalyptus or poplar. The logs are cut to size and then softened by hot water immersion or steam treatment to facilitate debarking. The softened logs are processed in a rotary lathe, where they are rotated on a sharp blade to create continuous panels. These panels are then cut to the desired size and graded based on their surface quality. Since the panels are still damp, they are dried in a hot kiln to reduce the moisture content to around 6 to 8%, ensuring proper bonding and preventing future distortion. Once dry, the adhesive is applied to the panels using a roller coater. Common adhesives include phenol formaldehyde, PF for outdoor plywood, and urea formaldehyde, UF for indoor applications. The plywood layers are then assembled with alternating grain directions, usually odd-numbered layers such as 3, 5, or 7, to maintain structural integrity and balance. The assembled plywood layers are hot pressed in a large hydraulic press under high temperatures, typically 120 to 150 degrees Celsius, and pressure 0.7 to 1.4 megapascals. This process cures the adhesive and forms a strong, uniform plywood panel, After pressing, the panels are cut to standard sizes, sanded to a smooth surface, and inspected for defects such as delamination, voids, or uneven thickness. Depending on the end use, plywood may undergo additional surface treatments, including melamine lamination, phenolic film coating, or decorative hardwood coating. It may also be treated with fire retardant or water-resistant chemicals. In some cases, edge sealing is also applied to improve durability during transportation or outdoor use. Finally, the finished panels are cut and sanded into various shapes required for the design of the home. Plywood is widely used in construction, furniture manufacturing, and industrial applications due to its high strength-to-weight ratio, dimensional stability, and versatility. Its multi-layer composition makes it superior to solid wood in many structural and aesthetic contexts. It is also appreciated for its cost-effectiveness and ease of machining. The assembly process of the Canadian-style log house in Germany begins with precision placement of natural round logs, pre-cut and notched off-site. Each log is craned into position, interlocked using saddle notches and pinned for stability. Under the guidance of architect Dippel Ing. Alexander Braun, the structure rises layer by layer. Final steps include roof framing, ceiling joints, and interior finishing, ensuring strength, insulation, and traditional craftsmanship. The assembly of a Canadian-style log house in Russia, crafted from premium stone pine, zerbe, showcases traditional craftsmanship and robust timber construction. The process begins with transporting precisely milled and hand-peeled logs to the building site. Each log is pre-notched using saddle joints and lateral grooves to ensure tight fits and natural insulation. A crane lifts the logs into position, where skilled carpenters stack and interlock them with wooden dowels and sealant. The natural resin content and aroma of stone pine enhance indoor air quality and durability. Roof beams, ridge logs, and gable elements are added to complete the structural shell. Final steps include installing windows, doors, and insulation where needed, resulting in a durable, breathable, and aesthetic home suited for harsh Russian climates. The Link sawmill system is an advanced, automated line designed to efficiently process round logs into rectangular timber sections. The process begins at the log infeed station, where each log is aligned and centered for accurate cutting. A series of mechanical arms and sensors position the log precisely before it enters the first cutting stage. In this initial stage, chipper canters or circular saw blades remove the curved outer surfaces of the log, producing flat sides and creating a rough cant shape. The cant then moves through profiling units, where sideboards are separated from the main section using vertical and horizontal saw blades. This profiling step enables the production of multiple board sizes from a single log, depending on the desired yield and optimization goals. Following profiling, the central section is passed through a gang saw equipped with multiple parallel blades to further divide it into individual planks of consistent dimensions and surface quality. Each sawing unit in the line operates with high precision and is controlled by advanced software to optimize material yield, reduce waste, and ensure dimensional accuracy. After sawing, the boards are automatically sorted based on criteria such as thickness, width, length, moisture content, and quality. Some systems may also include scanners or vision systems to detect knots, cracks, discoloration, or other defects, improving the grading process. Finally, the sawn timber is conveyed to stacking or further processing stations, such as kilns for drying, planers for surface finishing, or gluing lines for lamination. The entire link line emphasizes speed, efficiency, and precision, making it ideal for industrial-scale lumber production and engineered wood manufacturing, such as CLT, GLT, or LVL. With its modular design and flexibility, the system can be customized to meet various production capacities, wood species, regional standards, and product specifications. Building a barrel sauna is a rewarding DIY project that 2 people can complete in just a few hours. While designs may vary slightly by size or style, from 2-person models to 8-person setups, the overall assembly process remains largely the same. Saunas can feature either a wood-burning or electric heater. Always consult the detailed instruction manual and follow the heater manufacturer's safety guidelines. Electrical components must be installed by a licensed electrician. Start by locating the drain stave, which should be installed first, at the center of the cradles, using 2-inch screws. Each stave has notches, or crows, on both ends to accept the front and rear panels. Arrange the staves evenly to the left and right for easier installation. Keep the cradles parallel and perpendicular to the staves. Begin placing additional staves on either side of the drain stave, tapping them gently with a rubber mallet to align the crow's grooves. Secure every other stave to the cradle using 2-inch screws. Once the lower half is in place, fit the front and rear panels into the crow's cuts and ensure they are level and plumb. Use a temporary stave across the top to hold the panel steady. Continue adding staves up the sides. Nail down every second or third stave until reaching the 10 and 2 o'clock positions. Beyond that, the tension bands will hold the top staves in place. As the sauna takes shape, install the heater, 7 inches above floor level, benches, and center support, if over 6 feet long. Attach the heater fence and backrests at a comfortable height. Wrap the metal bands around the structure, covering any visible nails, and insert the threaded rods into the brackets. Tighten nuts evenly until the bands are secure. Install vinyl thread protectors for safety. Finally, feed the light cord through its hole and mount the LED power pack. Attach the doorknob. Once everything is in place, your barrel sauna is ready for use. With proper care, it offers a relaxing and durable retreat for years to come. Always refer to your specific manual for model-specific instructions. The illustrated process depicts a fully automated roundwood processing line in a German timber plant, designed to convert raw logs into square or rectangular timber elements suitable for structural applications. The system handles logs with diameters ranging from 12 to 55 centimeters, up to 60 centimeters maximum, and lengths between 2.5 and 6.0 meters, operating at speeds of 30 to 100 meters per minute, depending on log size and processing requirements. The process begins with log feeding, step 1, where logs are loaded onto a conveyor system and automatically transferred to the infeed unit. A series of rollers aligns and rotates the logs to ensure precise positioning. In step 2, the logs pass through a centering and alignment mechanism that ensures the log is correctly oriented before further processing. Next, in step 3, the logs undergo preliminary shaping. This often includes debarking or profiling using rotary cutters to prepare a clean, consistent surface. This step ensures uniformity for the subsequent machining operations. In step 4, the logs are cross-cut to predefined lengths using circular saws or guillotine systems, allowing the removal of defective ends and standardizing product dimensions. In step 5, the logs enter a profile milling unit, which is the core of the line. High-speed rotary heads with multiple cutting blades shape the round logs into squared or rectangular timber profiles. This is typically done using a four-sided planar molder configuration, ensuring smooth surfaces and tight dimensional tolerances. Step 6 involves sorting and classification, where finished timber elements are automatically evaluated and separated according to size, quality, and intended use. Non-conforming pieces may be diverted for reprocessing or secondary uses. Finally, in step 7, the processed timber is transferred to a stacking and packaging area. Here, automated systems neatly arrange the timber into bundles, ready for drying, further finishing, or direct shipment to construction sites. This integrated system emphasizes speed, precision, and material efficiency, with the use of CNC-driven components and real-time monitoring to minimize waste and downtime. The modular layout allows for customization according to production needs, making it ideal for high-volume processing of structural timber for modern wood construction industries. In addition to structural timbers, this process may also support downstream integration with finger jointing, CLT production, or glulam lines, depending on factory configuration. It ensures both flexibility and scalability, making it a vital component in the modern engineered wood supply chain. Haus Landwirtschaftsbau specializes in the construction of agricultural buildings, particularly for livestock farming. A typical project includes a modern dairy cattle barn with 46 cow stalls, an integrated milk room, and a calf barn. The structure measures 6 by 17 meters and features laminated timber pendulum supports and prefabricated wall elements for efficient on-site assembly. The roof design uses shed-style rafters and insulated roof panels, ensuring good thermal performance and protection. Approximately 150 cubic meters of timber are used in the construction, emphasizing durability and sustainable materials. Additionally, A 6 by 18 meter hay storage hall is built with glulam saddle roof trusses and insert purlins, supporting a robust and weather-resistant structure. Haas is recognized for delivering high-quality, customized agricultural facilities that meet the practical and environmental demands of modern farming. GZ Holzbau focuses on a precise and efficient timber construction process. It begins with detailed technical planning using modern CAD software. Timber components are then prefabricated in-house using CNC machines to ensure high accuracy. On-site, the assembly of the structural frame is carried out, where the prefabricated elements are assembled and secured in sequence. For large structures such as machine halls, heavy components are lifted and positioned using cranes, allowing for fast and safe installation. Throughout the entire process, GZ Holzbau ensures quality, structural integrity, and on-time project delivery. The production of a glued laminated beam begins with the delivery and inspection of raw, sawn timber. First, the boards are cleaned using mechanical brushes and air jets to remove dirt, bark remnants, and coarse debris that might interfere with further processing. After cleaning, the timber is stacked in preparation for grading. Next, wood defects, such as knots, cracks, resin pockets, or discoloration, are marked either manually by trained personnel or automatically using scanning systems with cameras and laser sensors. These defects are clearly identified and precisely removed through a process known as defect cutting, which ensures that only structurally sound sections continue in production. The remaining clear wood pieces are temporarily stored in a buffer zone before finger jointing. At this stage, finger joints, interlocking, wedge-shaped cuts are milled into the ends of each lamella using high-precision CNC-controlled milling machines. These joints are then coated with a durable structural adhesive formulated for high load-bearing applications. The glued ends are pressed together in a finger joint press, forming long, continuous lamellas with uniform mechanical properties. These are then automatically stacked and forwarded to the next process station. At the gluing facility, outfitted with a modern press system installed in 2023, the lamellas are first pre-planed to ensure tight dimensional tolerances. Accurate planing improves bonding strength by creating flat, consistent surfaces. Glue is then evenly applied to one or more faces of each lamella. The adhesive used is typically a polyurethane or melamine-based resin, offering long-term durability and moisture resistance. The prepared lamellas are layered according to the desired layup schedule, carefully observing grain orientation to enhance structural performance. Once the layup is complete, the entire assembly is placed into the hydraulic press. The press is closed and holds the lamellas under tightly controlled pressure, temperature, and time to ensure full curing and strong adhesion. Press parameters are continuously monitored to meet safety and quality standards. After curing, the resulting glued beam is removed and conveyed to the machining section. Here, the raw laminated beam is automatically fed into a four-sided planing machine. This machine precisely shapes all four sides of the beam, producing a smooth and accurate cross-section. Edge chamfering may also be applied to minimize splintering and improve handling during installation. The planed beams undergo another automated stacking process in preparation for final steps. To conclude the production cycle, the beams are packaged, either shrink-wrapped or banded, and labeled with batch and certification information. They are then stored in a climate-controlled warehouse or staged for direct shipment. Throughout the process, quality checks are conducted at each stage, ensuring the finished product meets structural, dimensional, and aesthetic requirements. These glued laminated beams are now ready for use in modern timber construction, offering high strength, dimensional stability, and architectural flexibility. The construction of the blacksmith workshop followed a precise, plan-driven process based on the architect's specifications. The workflow began with a dimensional inspection of the concrete foundation to ensure accuracy before mounting structural components. Timber wall panels were carefully aligned and installed to establish load-bearing capacity for the overhead ceiling system. Since not all internal walls were in place during early stages, temporary bracing was installed to maintain structural stability. The ceiling was assembled using BSB panels, chosen for their strength and reduced vibration performance. Installation of the upper floor mirrored the process of the ground level but required integration of additional components, such as a continuous vapor barrier. This barrier was pre-installed and sealed at all joints to ensure airtightness and prevent moisture intrusion. The roof structure was reinforced using structural screws and cross-bracing. Wood fiberboards were then mounted as the sublayer for facade membranes and roof underlays, simultaneously enhancing thermal insulation and structural rigidity. The careful sequencing and precision allowed several elements to be reworked or upgraded during the build. Overall, the success of the project relied on exact pre-planning, disciplined assembly, and favorable weather, resulting in a structurally sound and high-quality artisanal workshop. The construction of a wooden house begins with site preparation and foundation work, typically using concrete footings or slabs. Next, prefabricated or custom-cut wooden elements such as beams, columns, and wall panels are delivered. The structural frame is assembled on-site, starting with floor joists, followed by walls and roof trusses. Cross-laminated timber, CLT, or solid wood panels may be used for added stability. After the main structure is complete, insulation, waterproofing, and roofing materials are applied. Openings for doors and windows are installed, followed by interior partitions. Electrical and plumbing systems are integrated within wall cavities. Finally, interior finishes such as flooring, cladding, and painting are completed, resulting in a fully functional and energy-efficient wooden home. To begin, a guideline is marked on the tabletop to indicate where the plywood lies beneath. Using a turbo plane, the sides are planed down freehand to approximately ½ an inch above the line, maintaining a rough parallel. After all 4 sides are shaped, tape is applied around the top edge, and epoxy mixed with sawdust is used to fill voids between the end grain pieces. This mix creates an opaque surface, concealing the plywood beneath. The turbo plane proves extremely effective for rapid material removal and surprisingly flat results. By rotating it in a circular motion, high spots are easily detected and leveled. Once filled and cured, the top can be machined without risk of splitting. The result is a stylish coffee table with exposed end grain and epoxy inlays. It showcases the precision and efficiency achievable with the turbo plane, ideal for modern handcrafted furniture builds. What you need is the same as the Wood-Mizer LT50. The LT50 has a fully hydraulic wood processing system, including the wood machine, handle, clamp, and balancing roller, allowing a single operator to handle heavy logs with precision and minimal effort. Once the log is secured, the cutting head, equipped with a highly calibrated finish, is adjusted to the desired height for the initial cut. The operator will straighten forward, making the first angled cut to create a reference surface. With each cut, the head is lowered incrementally to create uniform panels of a specific thickness, typically ranging from 4/4, 1 inch, to 8/4, 2 inches, depending on the intended use. The LT50 does more than the LT50, minimizing waste and increasing productivity. As the wood is cut, the beautiful grain and color of the black cherry will be revealed. The boards and planks are removed and stacked with spacers to allow air circulation. At this stage, the selected pieces for refinement are inspected for technique and precision. The cut boards are cut down and stacked with spacers to allow proper air circulation during drying. Throughout the operation, the horn tension, feed rate, and lubrication are carefully managed to ensure clean, precise cuts with minimal wear. The result is high-quality, dimensionally uniform black cherry lumber, ready for seasoning or kiln drying. This wood turning project demonstrates the process of turning a segmented wooden vase on a lathe. The vase, measuring 9 inches in diameter and 12 inches tall, is constructed from 18 precisely glued rings, comprising a total of 432 individual segments. The woods used include mahogany, maple, walnut, and cherry, offering rich color contrast and grain patterns. The video tutorial covers the full setup, including how the vase blank is mounted securely between the lathe chuck and live center. Viewers will observe the turner's tool selection and techniques for rough shaping and fine detailing. This segmented turning project not only showcases advanced craftsmanship, but also serves as a great skill-building exercise for experienced woodturners. Segmented turning requires careful planning, precision gluing, and steady hand tool control, making it both a rewarding and technically demanding form of wood artistry. The Nesto 5-axis Ultra CNC wood lathe machine is a high-performance, computer-controlled turning solution designed for complex wood shaping and finishing. Equipped with a 5-axis control system, this machine allows for precise multi-dimensional operations, accommodating the production of intricately contoured components such as furniture legs, balusters, and artistic wood forms. The machine comes standard with multiple cutting and shaping tools, including a gouger with interchangeable blades, such as triangle and rounded blades. It also features a shaper blade, debarker, for initial rough profiling, and an oscillating sanding unit for surface smoothing during the same production cycle. These tools work in synchronized motions under CNC guidance, ensuring consistent geometry and surface quality. As optional features, users may include a detailed sanding unit for finer finishes and an automatic loading unit to boost production efficiency and reduce manual handling. A built-in spindle motor with a 5-position tool-changing magazine expands the machine's capabilities, supporting additional milling, drilling, and shaping operations beyond standard lathe functions. Thanks to its integrated sanding system, the 5-axis Ultra can deliver components that are fully finished, eliminating the need for separate post-processing. Once machining is complete, the finished workpiece is automatically ejected via a conveyor system, streamlining the production workflow. Designed for industrial-scale manufacturing, the Nesto 5-axis Ultra CNC wood lathe offers high accuracy, automation, and versatility, making it ideal for woodworking businesses aiming to produce complex forms with minimal labor input and high repeatability. The CNC Wood Lathe BYS 2100 is a precision machine designed for wood-turning operations. It features advanced CNC technology, offering high accuracy and efficiency for creating detailed wood products. With a robust construction and powerful motor, it supports various wood-turning tasks such as shaping, sanding, and carving. The machine's user-friendly interface allows for easy programming and operation, making it ideal for both small-scale workshops and industrial applications. The BYS 2100 is equipped with a versatile tool holder, adjustable speed settings, and an automatic feed system, ensuring consistent quality in every piece produced. Its durable design guarantees long-lasting performance in demanding environments. Modern high-speed CNC wood lathe machines feature a Siemens control panel for precise operation. Equipped with a sanding unit, a ball cutter for rough turning, and a triangular cutter for detailed work. The automatic tool length calibration device and 5-tool automatic changer enhance efficiency. Powered by an 18,000 RPM Arel spindle motor, the machine excels in complex wood processing. Meeting industry standards, it optimizes production with superior accuracy and speed, making it ideal for high-precision woodworking applications. At XL Furniture, chair production starts with an ecological approach to resource management. The wood is sourced from certified sustainable forests, and each species is selected based on its mechanical performance and aesthetic character, demonstrating a deep respect for the natural properties of wood. The fully automated production line forms the core of the manufacturing process. It begins with computer-controlled panel saws and CNC routers that cut timber into precise dimensions for legs, rails, and backrests. These machines operate on pre-programmed digital models, CAD/CAM, allowing exact repetition and reducing offcuts and waste. Following rough cutting, CNC milling stations create complex joinery, such as mortises, tenons, and dowel holes. These joints are essential for structural integrity and are produced to tight tolerances. Edge banding machines then apply veneer or ABS edging to visible surfaces, ensuring smooth transitions and added durability. Once parts are shaped, they move via automated conveyors to sanding stations, where robotic arms with oscillating sanders finish surfaces to a consistent smoothness, preparing them for finishing. Each part then passes through automated spray booths, where people nozzles apply stains, lacquers, or paints in controlled environments, ensuring even coverage and fast drying. Despite the automation, expert personnel remain vital. Operators monitor the system in real time, adjusting machine parameters and inspecting output quality. Manual intervention is also used in areas requiring touch-sensitive feedback or aesthetic judgment, such as final assembly and edge detailing. In the final stages, components are joined using automated dowel insertion machines and hydraulic presses. Every chair is inspected, assembled, and securely packaged, a process Excel considers integral to product quality and brand reputation. The result is a chair that combines industrial precision, human expertise, and sustainable values. The production of Velázquez furniture follows a comprehensive and meticulously organized process that integrates precision woodworking, fine detailing, and premium upholstery. It begins at the wood storage area, where raw lumber is stored under controlled conditions to maintain material integrity. Selected wood is then brought to the wood selection area, where quality and grain patterns are evaluated for consistency, density, and structural strength. Once selected, the lumber enters the cutting area, where it is dimensioned according to digital design specifications using industrial saws. This is followed by the router area, where CNC routers shape the wooden components with high accuracy, producing intricate curves, slots, and connection points. After shaping, parts go through the sanding area to smooth surfaces and remove splinters or tool marks, preparing for assembly and finishing. Carpentry continues in the carpentry area, where structural frames are assembled and bonded. Each component undergoes first detailing and filling to cover imperfections such as knots, pores, or minor cracks. Afterward, parts enter the lacquering area for the first coating phase, which improves both durability and visual quality. Attention to material preparation and small surface corrections at this stage ensures the long-term performance of the final product. The first assembly area is where frames and base structures are fitted and clamped together using wood joinery techniques and industrial adhesives. Simultaneously, the upholstery warehouse houses premium fabrics, leathers, and synthetic materials used in the sewing area, where trained seamstresses cut, sew, and finish textile covers with precision. Upholstery components are padded, stitched, and prepped in the upholstery assembly area, ensuring ergonomic comfort and a refined look. Specialized techniques, such as capitone upholstery, are handled with exceptional craftsmanship, adding deep tufted textures and luxury details. In the upholstery section, cushions, padding, and finished textile layers are integrated into the wooden structure. Each assembled unit then passes through detailed inspection, followed by a first sanding to refine edges, joints, and surfaces, ensuring finish uniformity and tactile smoothness. Next is the primer coating area, where an initial base coat is applied to seal the wood pores and enhance adhesion for subsequent layers. Once dry, a second sanding is conducted to achieve an ultra-smooth surface before moving to the staining area, where pigments or dyes are applied to enrich the natural wood grain. After staining, the furniture proceeds to the final lacquering area for the top coat application, ensuring resistance to scratches, moisture, and UV damage. After lacquering, each product undergoes final assembly to integrate all components: the wooden frame, padding, fabric, and hardware. This is followed by a final quality check, ensuring that each piece meets Velázquez's stringent standards in design alignment, structural integrity, and surface aesthetics. Special attention is paid to seam accuracy, fabric tension, edge finishing, and visual uniformity. Once approved, products move to the packaging preparation area and are then secured in the packaging area, using protective wraps, corner guards, and custom boxes to ensure safe transport. Completed furniture is temporarily stored in the chair warehouse before shipment. Logistics and delivery are managed by the Logistics and Transport Department, which coordinates national and international shipments with tracking and documentation. The entire process is supervised, under the leadership, who ensures that all departments operate in synergy and uphold Velázquez's commitment to craftsmanship, durability, and client satisfaction. From raw material to the final packaged product, every detail is managed with precision, tradition, and modern industrial techniques. At Johann Offner Holz Industry in Wolfsburg, Austria, the advanced link profiler line revolutionizes the processing of large-diameter logs, delivering precision, speed, and efficiency in heavy timber production. The system is designed to meet the rigorous demands of modern sawmilling through smart automation and high-performance technology, ensuring consistent quality and sustainability. The profiling process begins with a large log entering the link profiler line. In the initial stage, a set of high-speed cutting heads with serrated blades engages the log. These heads, positioned strategically around the log, remove the outer layers in a single pass, shaping it into a uniform cylindrical form with minimal material loss. The cutting heads operate at high speeds, ensuring rapid processing while maintaining precision to prepare the log for further refinement. In the next phase, additional cutting heads equipped with specialized tools, such as triangular and ball cutters, come into play. These tools are designed for detailed profiling, refining the log's surface and creating precise geometric shapes as needed. The triangular cutters handle intricate detailing, while the ball cutters smooth out rough areas, ensuring a polished finish. Multiple heads work simultaneously, enhancing efficiency and reducing processing time for high-volume production. The final stage involves further shaping or splitting the log into smaller, uniform timber sections. Serrated blades, arranged in a circular configuration, cut through the log with precision, producing consistent dimensions for various applications. Throughout the process, automated tool positioning and real-time monitoring systems ensure optimal performance, adjusting the cutters dynamically to account for variations in log diameter and wood density. This minimizes waste, maximizes yield, and maintains high-quality output. With its ability to handle large logs efficiently, the link profiler line at Johann Offner Holz Industry sets a benchmark in the timber industry. By combining advanced profiling technology with sustainable practices, It ensures the company is well equipped to meet future sawmilling demands while delivering reliable, high-precision results.